All right, welcome. My name is Ryan Hoger with Temperature Equipment Corporation, and this week's weekly webinar is Variable Refrigerant Reflow Systems with a specific focus on energy and energy standards. I do want to do a couple quick housekeeping things first. I know some of you guys are attending this in order to receive PDH credits. This is qualified for PDH credits in Illinois and in Wisconsin. It may be available for other states if you self-report and their rules allow it, but I know we're good for Illinois and Wisconsin. In order to receive PDHs, you do have to answer the quiz questions as we go. I'll pop them up on the screen. They won't be too hard, but you'll have to pay attention in order to answer them correctly. And there's also a portion of this GoToMeeting webinar service that we use that does an attentiveness tracking thing. Basically, it installs cookies on your computers and tracks whether you're doing multitasking things or whether you're paying attention to the webinar. So I highly recommend, in order to get a good score in that regard, you shut down Outlook and all of your other distractions. Just do the webinar and only have that open on your computer. The more stuff you have open, the more they ding your score and the less likely they will award you the PDHs. All right, with that being said, let's go ahead and begin. Here's our agenda for the next hour here. First, we're going to do a refresher on Vrf Technology. We're not going to spend a lot of time on that. I'm assuming by now, over the past 10 years, everybody's seen the Vrf 101 type presentations and has that beaten into their head. We'll just do a quick refresher so everybody's on the same page. Then we're going to talk about Hri standard 1230, which is the quote-unquote new rating system for Vrf systems. And by new, I mean it's 5 years old. But for us in the real world, that's pretty much new. We'll talk about the Ashrae energy standards that apply to Vrf and how they work and what you have to do. And then, even though it's not related to energy, we'll talk about Ashrae 15 refrigerant safety because, well, we got a lot of Ashrae stuff in here, so why not squeeze one more Ashrae thing in? I've done this exact presentation for the Ashrae chapters in Milwaukee, South Bend, Northwest Indiana. So I realized I hadn't done it for the Chicagoland folks at all, so the webinar seemed like the easiest way to do that for a bunch of people at one time. So that's why we're doing this today. But it's basically an Ashrae ready presentation, so there's no branding or anything like that in here, except for if you can read the tiny logos of the units in the corner there. So what is VRF? VRF, as most of you guys know, stands for Variable Refrigerant Flow Systems. One manufacturer also calls it VRV, and that's become kind of a Kleenex type term. But the official name is Variable Refrigerant Flow Systems. What this basically means is I have a single outdoor unit serving multiple indoor evaporator coils. Sometimes we also even have 2 or 3 outdoor units, manifolded together refrigerant-wise, serving multiple indoor units. So we run these outdoor units at different speeds, and the indoor units will use as much refrigerant as they need. And if they need less, they tell the outdoor units, hey, we need less refrigerant volume, slow it down. One of the cool things about this is you can mix and match all the indoor units. So you can have, cassette style units in the ceiling grid. You can have ducted units with a little bit of duct run on them. You can have consoles on the floor. You can have the duct-free split high wall type units. All those can be mixed and matched on the same building. And sometimes you can also mix and match heating and cooling zones at the same time. All these types of systems from all of the manufacturers have built-in controls to them. Right, so every single indoor unit has its own control system built into it. All the outdoor units have their own control systems, and they all use proprietary communication to send data between the indoor and outdoor stuff. So you cannot mix and match brands. You can't put manufacturer A's indoor stuff on manufacturer B's outdoor stuff and vice versa. You also cannot use your own third-party control systems. You can have third-party controls integrate to these, but you can't gut them and put your own controls in, at least not within the warranty. Typically, for most manufacturers, these VRF systems come in 2 flavors. The quote-unquote traditional system is referred to as a heat pump. Some manufacturers call that 2-way or 2-pipe because we use 2 pipes. The other type is heat recovery, also referred to as 3-way or 3-pipe because we use 3 pipes. And just for a point of note, there's actually a 3rd and a 4th pipe in both those scenarios for your condensate line, but we're talking about the refrigerant pipes in this case. So here's really the main reason why these systems are becoming more popular. If you look at a typical air side system, a VAV zoning system, if you will, air as a heat transfer media can handle about 7 BTUs per every pound of air. A hydronic water system, a chilled water system, can handle 20 BTUs for each pound. A refrigerant-based system, it's 116 BTUs per pound. So we can move a lot more heating and cooling energy around the building in a lot less given space, using a lot less distribution energy. That's really the big benefit here. Another way to look at it is in reverse, right? So I can say that a refrigerant line set of 7/8 and 3/8 diameters can move the same amount of energy as 2-inch chilled water pipes, which can do the same amount of energy as a 16 by 48-inch duct. I don't know who made this slide for me, but we don't use 49-inch duct, so I'll say 48. So 16 by 48-inch duct, which is a fairly decent size, is the same as a small refrigerant line less than 1 inch. So we can move a lot of energy around. And visually, it might look like this. This is a 40-ton refrigerant piping network sitting right next to a 12-ton ductwork system. And you can see there's just, even though it's 3 times as many BTUs, it takes up, a third of the space. So that's kind of the ratios we're looking at here. So it's really good for retrofitting systems where I want to move things moving around the building, energy moving around the building without having to rip a lot of stuff open, and I might not have the space for a lot of ductwork. So real basic here for a couple more slides. It's important to note that all VRF systems are heat pumps, at least in the United States. There are cooling-only VRF systems in existence. Nobody has one in the U.S., so at least not that I'm aware of. So for our purposes here today, every single VRF system is a heat pump. So you need to understand a little bit basics on how a heat pump works. So when we talk about all these ratings in a little bit, it all sort of makes sense. All right, looking at a simple house example up here on the top, I have my indoor evaporator coil in my house, and his job is not to make the air cold. I realize he does that, but his real job is to suck heat out of the air. It is to remove the heat from the air. So he removes that heat, he sends it through the refrigeration network to the outdoor unit, and his job is to reject the heat and dump it outside. So we suck heat from your building and we dump it out into your yard. Suck heat from your building and dump it out into your yard. That is what a traditional AC system does. And by the way, the indoor temperatures that we're working with, let's just say it's 75 degrees inside and it's 90 degrees outside, I am literally sucking heat from the cooler air and dumping it to the hotter air. It's kind of a little bit of a tricky thing. We got to use the refrigeration cycle to do it, obviously, but that's what an air conditioner does. A heat pump is an air conditioner also, but we switch the jobs of the evaporator coil and the condenser coil in the wintertime when we need heating. So my outdoor unit is my condenser coil. My indoor unit is my evaporator. I'm still pumping the refrigerant between them. Just things are just going in reverse, right? So it's 10 degrees outside in this case, and it's 70 degrees inside. And I'm moving heat from the cooler air source outside and dumping it into your building, right? Just like I was doing in the summertime. I was moving from 75 to 90. Now I'm moving from 10 to 70. All the heat pump is an air conditioner that runs backwards, and the evaporator and condenser coils literally switch jobs. Other than that, it's an air conditioner. All right, so let's just keep that in mind as we're going along here. Let me clear that out and switch back to my mouse. If anybody has any questions as we're going along, you can just type them in the question/chat box there, and I'll try to answer them as we go. So that's what a regular VRF system is. Let's just discuss what a heat recovery type system might look like. So in this particular case, on the left-hand side, I have a outdoor unit right here circled right now, and then I have 5 indoor units. 1, 2, 3, 4, 5. I'm a fantastic artist, as you guys can all tell, obviously. So in this case, it's in the heating mode. So I have I got 10 tons of heating need connected to an 8-ton outdoor unit. That's very common, right? Just like with a VAV system, we take advantage of the diversity credit. Every single zone doesn't need max heating and max cooling at the exact same moment in time, so we can take some diversity credit. Actually, this time we didn't do that. We have 8 tons on 8, so we could have done that. We should have used a 6-ton unit probably. But what happens here, everybody's in heating mode, so all the indoor units are condenser coils, and the outdoor unit is the evaporator coil. When I switch this guy into a different mode, let's say everybody doesn't need heat. In this case, I got 2 zones that want cooling for a total of 4 tons, 1 zone that wants heating for a total of 1 ton, right? So I need 5 tons of heating and cooling. But what I do is I close down my valves in the outdoor unit, So I only use 3 tons of the condenser coil surface area. And then in this case I have 2 compressors. I'm only going to pump 1 compressor, in this case at 4 tons. I need to move 4 tons of refrigerant for those 2 zones that want 2 tons of cooling each. So I got 2 zones that want 2 tons of cooling, right? Those guys are going to reject 3 tons of their heat rejection outside of the outdoor unit, and they're going to reject that 4th ton into the zone that wants some heating, right? So I've always got as many evaporator coil surface areas as I have condenser coil surface areas, if you will. So I'm getting 2 tons of cooling for the heat rejection price of 3 tons for the compressor pumping power of 4 tons. Right? I'm getting 5 tons of total work done here. This is why these systems become very efficient when you put them in the heat recovery mode. Instead of running a furnace or a boiler to do that heating, I'm just taking some of my waste cooling heat and dumping it over into that heating zone. That's the basic premise with this here. And then likewise, if I have more heating zones than cooling zones, then it works a little bit differently. In this case, I have 1, 2, 3, 4, 5, 6 tons of heating, and I need 2 tons of cooling. Right? So my condensing unit goes into the heating mode. So I'm grabbing 4 tons of heat from the outdoor air. I'm pumping 6 tons of compression to move those 4 tons into my zones. And I'm grabbing my other 2 tons of heat from my zone that wants cooling. Right? So I still have 6 tons of cooling going on and 6 tons of heating going on. Just choosing which zones I dump them into. So I'm getting a total of 8 tons of heating and cooling effect for the heat rejection price of 4 tons for the compressor pumping power of 6 tons. And then, of course, if the heating and cooling zones ever matched up perfectly, which is very rare, obviously, then I would shut off all the coils in the outdoor unit, and I would reject nothing outside, and I would take nothing from outside, and I would just have 4 tons of heating, grabbing their heat from the 4 tons of cooling zones, and my compressor would basically be like a circulating pump, right? And that would be a super efficient scenario there. All right, so kind of the summary of the technology, so we can talk about the energy stuff. You can have lots of indoor units connected to, dual or single outdoor units. In some cases, even 3 outdoor units can be manifolded. But you got lots of indoor units connected to one refrigerant network served by one condensing unit system or modules. You get very high heating performance, and we'll talk about that here in a minute. You can do simultaneous heating and cooling, right? So I can have one system providing cooling to some zones and heating to other zones, and that does yield very high efficiencies. I can only do the simultaneous when I have the 3-pipe type systems. I can have individual zone control just like I do with the VAV system, and arguably perhaps even smaller zones in some cases. But I can have individual zone control, so each one of my tenants or offices or whatever can have their own thermostat and get the heating and cooling that they want. Typically, install costs are lower than the 4-pipe fan coil system, and typically they're higher than a rooftop system. That's not always the case, right? Depends on, is it an existing building, not existing building, how much space do I have available to me, right? But those sort of things. But from a first cost standpoint, out of the box, on average, the highest price point thing would be a hot water, chill water fan coil system. Then we would drop down to a VRF system, and we would drop down in price to a rooftop, a VAV rooftop system. But depending on your existing building, that could change. One other nice thing about a VRF system, if you're trying to get higher efficiency systems without having to have hydronics involved, you can get rid of the cooling tower and obviously the chemical treatment of the cooling tower and all the makeup water for the tower and the boilers by going with one of these refrigerant-based systems. Additionally, you can also save some floor area because you typically don't have mechanical rooms. You have small zone units that are in above the ceiling or on the wall instead of in closets taking up space. You have a single source supplier for your controls. Your equipment manufacturer and supplier is your controls manufacturer and supplier. It's all integrated in one and the same. And the sound levels are very, very, very low for both the indoor and the outdoor equipment. That gets proven out pretty easily. And then you have some redundancy in terms of your compression. If you have tandem units connected together and you want to service one, you can still run the other one in some cases while you're servicing the first one, depending on what problem you're trying to solve. All right. Do we have any questions thus far? Let's do a poll question. I'll launch that right now. All right. So the poll question is, what fluid can transfer the least amount of heat? A, water. B, water with glycol. C, air. D, refrigerant. I'll give you guys a little bit of time to answer that. If you want to type any questions in for me to try to answer, you're more than welcome to do that, and I'll look at those right now. Looks like 71% of the people voted, so we'll give it another 10 seconds or so we get the rest of the votes. All right, I'm going to close the poll down in 3, 2, 1. I think we got pretty much everybody. So it looks like you guys did a good job. We got the right answer. Let me share that result with you on the screen here. Hopefully you guys can see that right now. And 95% of you said air was the least efficient at transferring heat amongst those 4 choices. And you are correct. Air is a very difficult heat transfer media to work with. We use it all the time because we have air in all of our rooms, so we do it, but it's not the easiest way to do it. All right, go back to our slides here. All right, so let's talk about the efficiency of some system types. Before we do that, real quick, Robert types a question in, how do you handle very cold outdoor ambience lower than -10 to -15 degrees? So there's a couple different things that we're going to do in that regard, and it's really for the VRF 101 topic. Usually what we're doing, if you have those types of ambient design conditions, which, by the way, we do not have in Chicago, our design condition is only like -3. But usually if we have very cold temperatures we're dealing with, we're typically talking about hybrid systems that have another heating source involved in them. That heating source could be an electric resistance backup. It could be, I guess, theoretically a gas furnace, so that would be uncommon on VRF. It could be a hydronic system. A lot of VRF installs go into retrofit scenarios on buildings that have heating only and they've never had cooling before, and now we're adding cooling. So they typically have hydronic radiators and baseboards. That works out very nice in this case. You can design your VRF system to be around the cooling mode and let the hydronic system make it up the difference when it's really cold. And then also you can design your VRF system for very cold ambience, but that does lead you to very, very large condensing unit sizes, or outdoor unit sizes, I should say. And it's not very common that people are designing for -10 degrees with their VRF by itself, but it is physically possible. Robert chimes in also, -3 is designed, but we also had a week last week when it was -14 in the Midwest here. That's true, and you'll also have a day when it's -19 and -22 and all that stuff. From a design standpoint, we should not be looking design for the worst case day. We should be looking for that 99.6, 99.9%, Ashrae weather day. That's a separate debate. The last thing before we move on, Syed says that air is not a fluid, and I would certainly argue that it definitely is a fluid. I don't know how to describe that differently, but air is definitely a fluid in motion. We're pumping it around the building. All right, so back to efficiencies. So looking on the screen here, we're showing some typical efficiency ratings that you see for different pieces of equipment for the cooling side, and we'll talk about heating separately. The first thing to understand is that almost all pieces of equipment are rated and or tested to AHRI standards. AHRI is the American Heating Refrigeration Institute. So it's basically all the manufacturers getting together and deciding what the rules are for rating this stuff and then publishing all that stuff online for people to use. One interesting thing that happens on these systems is that each type of product gets its own rating system, which has absolutely nothing to do with any of the other products. So it's basically virtually impossible to use these rating systems to compare a chiller against a rooftop, against a condensing unit, against a boiler, against a VRF system, against a furnace. You cannot compare one to the other directly. I don't know if that's just the way it worked out or that's on purpose. I'm not sure. These rating systems are really good, however, at comparing the same system type, manufacturer A to manufacturer B, or even the same manufacturer, choice A to choice B. Right? So if I want to look at 2 rooftops and compare them, and this is a good way to do that. If I want to look at 2 chillers and compare them, this is a good way to do it. If I want to compare an air-cooled chiller to a water-cooled chiller, probably not the best way to do it. If I want to compare a boiler to a VRF, definitely not the best way to do it. However, with all that being said, what I try to do with some of these rating systems is I try to convert them to an approximate equivalent COP. So we can kind of compare them just on a discussion basis. So for small split systems that are 65,000 BTUs or less, which is 5 tons, those systems are typically rated with SEER, S-E-E-R, which is the residential rating system, even though I know we use 3, 4, and 5 ton systems commercially. And even packaged rooftops are rated with SEER, 5 tons and under. You can see the COP range for cooling is that 3.5 to 4.5 type range. COP is coefficient of performance. how much electricity and fuel sources did I buy versus how much did I get out. So how much energy did I bring into the piece of equipment, how much capacity did I get out of that piece of equipment. It's a direct ratio. So for every 3 kilowatt hours I buy from the electric utility, every 1 kilowatt hour I buy from the electric utility, I'm getting 3 units of equivalent energy out of it. It's 320% efficient to 430% efficient. When I get to larger stuff that's above 5 tons of capacity, we rate it in EER, energy efficiency ratio. It's a little bit different discussion than SEER. SEER takes into cycling and counts and all that. EER is just straight efficiency on design day if it were ever to happen, right? And we rated equipment that way for a very long time. More recently, in the past 5-6 years, there's been this massive movement on these systems to start using IEER, which is Integrated Energy Efficiency Radio. It's a part load rating, and we'll talk more about that when we talk about the VRF rating. But basically, it recognizes very seldom are you on a design day. You're almost always on a part load day. So let's start rating systems for the part load so they can be compared more fairly to one another. Air-cooled chillers are also rated in EER. You can't compare it directly to rooftops and DX splits because those units have the air distribution mechanism included, which is a fan. The chiller does not have the distribution mechanism included, which is a pump. So it's not a fair comparison, but just if we had to do it, I just, thrown up on the screen there's kind of your range. On the heating side, it's even less likely that you could try to compare something directly, but I try to do it anyway. Electric heat essentially is a COP of 1, which means it's 100% efficient. I know technically it's like 99.9 something, right, because a little bit turns into visible light. But for the most part, every kilowatt hour I buy turns into a kilowatt hour of heat. It's 100% efficient. A furnace or boiler, if I buy the best one that I could possibly find, which I believe on the market is a 98% efficient unit, that means for every unit of energy that I buy, I'm getting 0.98 units of energy out, right? It's less than 100% efficient. Now, natural gas is very cheap in our market, so it may be the cheaper energy source, to run your building at in some cases, but it's not going to be the least energy using source. Rooftops are worse off than the furnace and boilers because hardly anyone has a condensing rooftop. I know there's some test ones that are out there, some newer ones that we've worked with on our projects where we have condensing rooftops, but for the most part, 82% efficient is kind of your max best on a rooftop unit. And then you have heat pumps. For the small residential size ones, 5 tons and under, they're rated in Hspf. For sake of argument today, that's basically the SEER of the heating world. How efficient is your unit as we cycle it through the various modes of heating? The bigger stuff that's more than 5 tons of capacity, gets rated in COP, coefficient of performance. And it's very common to see ranges of those. In this case, 2 to 3.8 is the range I put up on here. And the temperature at which you choose to test it affects the coefficient of performance, just like it would on a cooling system. If we tested it at something hotter than 95 degrees out, it would lower the EER and COP numbers. For heat pumps, they test them at 47 degrees, and then usually they also test them at 17 degrees to give you an idea of how the energy and capacity are scaling. So what about VRF? How efficient is the VRF system in this discussion? That's really what we're going to look at here. Before we do that, I'm going to pop up our second poll question. Actually, I'm going to change the screen. Then I'm going to pop up the question so you guys can't copy the screen. All right, so what is the most efficient heating type on the list here? So our choices are electric resistance heating, heat pump, condensing boiler, gas rooftop. Now remember, we're talking about the most efficient, not necessarily the most cost-effective, the most efficient. For all the energy that I buy, who's costing me the least to run? Sorry, who's using the least energy to run, not necessarily cost. So we got a neck-and-neck tie with electric resistance heating and heat pump heating, with 85% of the people voting. I'm going to give it another 5 seconds, and then we'll shut the poll down here. All right, 3, 2, 1. All right, I'll put that up on the screen for you guys to see. Looks like the heat pump voters just barely beat the electric resistance heating voters at a 52% to 43% rate. Let's just go back one screen here. What was electric resistance heating? A COP of 1. What is heat pump heating? A range on this of 2 to 3.8. right? So heat pumps, even when it's very cold out, like 17 degrees, are twice as efficient as electric resistance heating. Heat pumps always beat electric resistance heating. The worst heat pump in the world on a minus 20 degree day is very likely still going to be over a 1.0 COP. Right? So heat pump is always going to beat electric resistance from an energy standpoint. So I don't know if I tricked you guys with that question on accident or what happened there. Let's go ahead and take that back off. All right, let's continue on. All right, so HRI finally has a rating system for VRF systems. I say finally because, you know, from 2006, 2007, when VRF started getting interesting in the United States, till 2012, 2011, we really didn't have a rating system. It was kind of like the wild, wild west. We would just say, hey, this is what we think the efficiency is compared to that, and how's that sound, right? All the manufacturers got together in like 2008, I think it was, and sat down and put together the standard for testing and rating this equipment, and that standard got published in 2012, and it is called Standard 1230 from AHRI. So that is the rating system that we're working with. If you've never been to the AHRI directory website, it's ahridirectory.org. It's a great website in terms of having tons of data. It's a horrible website in terms of searching for anything. So if you ever get stuck on that, let me know. I'll help you out. I'm getting fairly good at it one way or the other. But you can look at just about anything's capacity and efficiency by brand, by model number type of thing. So there's a residential category and commercial category. Just note that residential and commercial is the way they choose to list the products. It doesn't mean you can't use one and the other. So everybody knows we put small 3-ton DX split systems in a commercial building before. And everybody's probably heard of a job where we put a chiller in a house, right? That stuff happens all the time. So just kind of keep that in mind when you're looking at these lists. In case of VRF, it's under the commercial section, and you'll scroll down to the bottom of the list alphabetically down to VRF. When you click on it, you'll have a screen that pops up where you can search stuff. When I did this presentation about a year ago, I think it was, up on top is the box of available manufacturers that were listed on there, which was a lot of them. The box on the bottom is the one I did a snapshot on the screen this morning. You can see there's more manufacturers now that are rating it, and I would argue that it's pretty much every manufacturer that has a product in the U.S. is now using this rating system. So pretty much everybody's playing by the same rules now. This is what the search screen looks like. Okay, before we go on to that, let me just address this electric resistance heat pump thing, because a lot of guys are typing questions in and they seem to be confused. All right, so some folks are arguing efficiency and COP, right, as a percent. A COP of 1.0 is the same as 100% efficient. A COP of 2.0 is 200% efficient. A COP of 3.0 is 300% efficient. COP is just a direct ratio of how much energy did I bring in versus how much capacity in terms of energy did I get out. Now, a couple folks, you guys are typing in that you can't have anything above 100% efficient. That is completely and totally not true. You can definitely be above 100% efficient. And I will try to go back real quick and explain, just only because there's so many guys asking. I thought we could skip the VRF 101, but maybe we need just one more topic on it. When I am using a gas furnace or a boiler to heat your building or your home, or a rooftop unit for that matter, a gas-fired piece of equipment, I am burning a fuel to make heat. And some of that heat goes up the stack, goes up the flue, right? So those products that burn gas are never 100% efficient, unless you have a direct-fired piece of equipment with no ventilation air, in which case you probably die soon, right? But they're never more than 100% efficient. If I have electric resistance heat, all of the energy that I buy is being converted into heat, with the exception of a very small portion which gets converted to visible light, like when you look in your toaster and you see that little orange glow, right? So there's 0.1% of that, 99.9% is going into heat. In the case of a heat pump, I'm not burning anything to make heat. I'm only paying energy to move heat around. I'm not making heat, right? Furnaces, rooftops, boilers, electric heaters, they burn something. They convert a fuel into heat. Heat pumps do not convert anything into heat. They just pump heat around. They move it from outside to inside, just like your air conditioner does. Your air conditioner moves heat from in your house to outside your house. The heat pump moves heat from outside to inside. So on those really cold days in the winter, it's 10 degrees out or whatever, I'm looking for the heat that's available outside. I'm sucking it into my coil outside, and I'm pumping it into your building. Because I'm only paying to move the heat and I'm not paying to make the heat, it is significantly more efficient than 100%. In all cases, for all heat pumps, at all outdoor ambient conditions that you would experience in the Midwest. Now, if you go to the Arctic, okay, maybe this isn't true anymore, and maybe you do get below 100% efficient, but for everything else, the heat pump is going to be above 100% efficient, and it's always going to beat out the electric resistance heat. All right, so let's get back to the screen over here where we were with the Ahri rating system. All right, so you can search by manufacturer, you can search by types, you can search by minimum efficiencies, maximum efficiencies, capacity ranges. You got lots of stuff you can search for here. The one thing I will mention is that if you fill out every single thing on this screen, you likely will get nothing returning back to you as an answer. It's just very hard to do that. So I would say is pick a couple things to search by, hit search, see how many results you get, and if you get 10, 20 results, then you can scan through the list. If you get 1,000 results, hit the back button and refine your search a little bit tighter. That seems to be one of the best ways to use this site. And we'll show you what some of these different things mean on here. So the Hri System Type, which is the second field choice you have there are four types of types, that sounds great, available for VRF systems right now. And it's basically a jumble of alphabet soup and can look a little confusing because they don't do a good job describing what they are. There's only two letters you really have to look at. It's the fourth and fifth digit. So the fourth digit, if it's a V, it means it's a heat pump. And in the case of VRF, that means that it can be either in the cooling mode or in the heating mode, but it cannot do both simultaneously. If that fourth digit is an R, that means it's a heat recovery VRF system. That means it can do heating and cooling simultaneously. So some zones get heat, while other zones get cooling at the exact same time. So those two systems are rated a little bit differently from each other. The fifth digit is either an A or a W. A means it's an air-to-air heat pump. A W means it's a water-to-air heat pump. Right? That's the difference there. So do I have air as my sink source, or do I have a water loop, meaning a cooling tower and boiler, or even a ground source geothermal loop connected to my system? So VRR means heat pump or heat recovery, three-pipe system. A or V means air or water. The next thing you'll notice on this data is the EER, energy efficiency ratio, which we had mentioned. This is the rating system that we use for lots of different types of cooling equipment, and it's tested at full load cooling, which basically means we run the unit, full maximum at a steady state condition, and it's tested at 95-degree dry bulb. If your location only needs 89 degrees or you need 110 degrees, oh, sorry, we'd only test them at 95 is kind of the thing there. So it's really good for comparing one to the other, but it doesn't really tell you what's going to happen at your location. You can convert COP and ER directly because they're both steady state scenarios. If you take the ER and divide it by 3.4, you'll get the COP, right? So for sake of argument, let me see if I can pull that up on here. If I had something that had an EER of 12, I could take 12 divided by 3.412, and if I did it right, 3.412, my COP would be 3.5, which would be 351% efficient in this case. In addition to EER, we have IEER, which is the same thing that the air-cooled chiller guys are doing now, and the rooftops and the DX split systems, the larger ones, they're doing IEER also. That's the part load cooling efficiency. So what this does is it takes into account the fact that, well, how often are we running at max capacity and it's 95 degrees outside? Well, that doesn't happen a lot. I know we designed for that, but that doesn't happen a lot. So what this thing does is this tests it at 100% capacity, 75, 50, and 25% capacity. It's kind of the easy way to think about it. And then it weights those, right? So D, which is the 25% capacity, gets a 12.5% rating time. So 12.5% of the time, we're going to assume it's at that level. The C level, which is half capacity, we're going to assume it's there 24% of the time. The 75% capacity level, we're going to assume happens 61% of the time. And 100%, 95 degrees out, we're going to assume happens 2% of the time, which is almost nothing. So it's heavily weighted for the 75 and even 50% range. That middle range, it gets heavily weighted on because that's probably where you're going to spend a lot of your runtime. So that's how you get these IER numbers. The chiller and condensing unit guys do it similarly. I think the weightings are slightly different, but they test them in those 4 buckets, 25, 50, 75, and 100, to get you a part load efficiency rating. If you do anything with utility programs, not necessarily VRF, but just in general, like chillers and stuff like that, you'll notice that most of the utility programs don't even look at EER. They simply specify IER, because part load is where the action is at. EER is somewhat irrelevant because it's never really a full load day in most cases. You'll also notice that there's COPs on there for the heating mode. The heating mode is tested at 47 degrees outside and 17 degrees outside. The 17 degree number in almost all cases is going to be less than the 47. There are some units that have a quirky scenario where it could actually be higher, but that's a whole other debate and an irregularity. So usually as the temperature drops outside, so does the efficiency and the capacity at those levels. One thing to note on this heating discussion is that the COP of the heating is the COP of the heat pump heating. If you've chosen to use electric backup supplementary heat or a boiler or something like that for supplementary heat on a really cold day like Robert was asking about earlier, that energy is not included in the discussion. So really this is the COP, assuming you don't need any backup heat at that moment. So we got those 4 ratings, EER, IER, COP, and COP 17. Then we have a 5th rating for VRF because there wasn't enough rating systems, right? So unlike all the other products, there's 5 different ways these things are getting rated. It's the simultaneous cooling and heating efficiency. And because we're the HVAC industry, we got to make that into a 4-letter acronym, so it's SCHE. You may have seen that on stuff or on an engineer's spec or a schedule for VRF systems and not even knowing what the heck that meant. So I'm going to try to explain what that basically means when you see it in the rating system here. The SCHE is the ratio of the total capacity, meaning all the heating BTUs being delivered to zones, plus all the cooling BTUs being delivered to other zones, as related to the effective power when it's in that mode. For that particular test, they're assuming 50% of the zones want heat and 50% want cooling. So basically nothing's getting rejected outside. So it's the best possible case in time, right, like we showed before. This test is done at the 47 degree point. They don't do it at the 17 like the heating does, probably because they figure if half your zones need cooling, it's probably not 17 outside, so no reason to do the extra testing. The units of measure for SCHE are BTUs per watt hour, which is the exact same as the units as we use for EER and IER. So if you want to convert SCH to a COP at that instant in time, you would use that same formula I showed you before. The COP would be the SCH number divided by 3.4. That would give you the COP, right? So that's kind of your best case scenario. Now a bunch of questions came in, so I'm going to pause for a second and look at some of these questions before we move on. Just kind of want to get them answered while we're close to the right section. Robert said to clarify, he'd like me to clarify the cost of energy to operate gas-fired equipment versus heat pumps. Yes. So that's something that I did mention when we were talking about that. I was trying to be careful with that. Right now we're talking, when I had this screen up, we were talking about the efficiency of something. How much energy is being used. The amount of energy being used is not the same as the amount of money you're spending for the energy. If you use different fuel sources, natural gas, propane, coal, oil, electric, etc., all those fuel sources have different costs associated with them depending on what town or area that you're in. So a lot of times here in the Midwest where I live, in Chicago area, it is usually cheaper to heat with gas heating systems because gas is ridiculously inexpensive. Electric's like medium priced, although it feels painful when I pay my bill, but electric's like medium priced. Natural gas is super, super low price. So a lot of times a gas heating system like a boiler will beat out a heat pump in cost. That's true usually when you have heat pumps that are fixed speed. Now that we have variable speed heating pumps, residentially and with commercial VRF, that's not always true anymore. But this particular example here was specifically based on energy. And energy cost are two things that are not the same. That's a good point there, Robert. Thomas points out, because he's getting technical, the visible light from my toaster example or any electric resistance heater eventually does turn into heat when it reflects off of a surface, so, and then it gets absorbed into that surface. So he's probably right there. So maybe we could just go ahead and say the toaster and electric street heater really are 100% efficient. George asked if the presentation will be available. Yes. This is being recorded, so that'll be posted for coworkers to look at. And then if you need a specific slide or something like that, you want me to send it to you, just send me an email later. I'll give you my email at the end, and you guys can do that. Andrew asks if the EER weighting is the same for other technologies, and no, it is not. It seems like all the manufacturers, whether it's the chiller group, the DX group, or the VRF group, they have slightly different weighting factors on these capacities that I'm showing here. They're close. They do heavily weighted at the 50 and 75 point, and they put very little weight on the 100 and 25% weighting points. But the exact weighting multipliers are not identical to other technologies, but they're close. Jeff asks about the significance of the 17 degrees for testing. The reason that we do it on heating systems, and this is for all heat pumps, not just VRF, we rate them at 47. And the reason it's 47, by the way, is because that traditionally, a long time ago, when we had certain temperatures we expected indoors, that 47-degree rating point for heating gave us approximately the same delta T across the heat exchanger that a 95-degree cooling scenario would have given us. So that's kind of how that 47 number evolved. The 17-degree number evolved into these rating systems decades ago because people recognized, well, I'm going to run my heat pump when it's less than 47, and because there's less heat available in the outdoor air, I'm going to get less capacity, so I need to know what's going to happen. So they just randomly chopped 20 degrees off the rating number and did that testing point as well at 17 degrees, so you can kind of see that temperature dropping. Yeah, in the perfect world, they tell us the capacity difference and efficiency difference at every single outdoor condition, but that would be a lot of testing to do. So they give us 47 and they give us 17. Andrew mentions that asks if the outdoor temperature matters on the 50-50 scenario. And to be quite honest, until you asked that question, Andrew, I never really thought about it. But you're right. If I have 50% of my zones in heating and 50% of my BTUs going into cooling and nothing's really going to the outdoor coil, it doesn't really matter. I guess it only matters slightly for whatever distance of piping I have sitting on the roof and the heat of the compressor itself. You know, other than that, it probably doesn't really matter. So you really don't need to test it at multiple outdoor conditions. That's a good point. I never thought of it that way, Andrew. Dennis asks how Hspf correlates with COP and EER. So COP and EER can be directly converted from one to the other. Like I mentioned previously, the COP is the EER divided by 3.412. Hspf, and for that matter SEER, can never be converted into EER or COP directly because the SEER and Hspf tests, which are for small residential equipment, 5 tons and under, those tests have seasonal performance equated into them. So what they're doing is they're taking into account cycling losses of this equipment turning on and off at different temperatures. And they also take into account things like Hspf takes into account things like supplementary heat and defrost cycle on a heat pump as well. So COP and EER are just straight up, let's run this at a steady state condition at the max design scenario and see what I get. Hspf is trying to be more realistic, and it's cycling things on and off and taking into account those inefficiencies of doing that. So you cannot really correlate Hspf directly to COP and EER. However, what I did here is I tried to do my best guess math at looking at different tables of pieces of equipment that are rated both ways sometimes. And an Hspf of 7 is approximately a COP of 2. An Hspf of 13 is approximately a 3.8 COP. It's approximate because you can't directly convert. All right. I think we're good with questions for now. All right. Let's do another poll question. This one hopefully will be a little bit more straightforward. It's a true-false question. So read the whole question before you click on it. All right. Why is my thing's blocking here? Okay, well, I'll try my best to just, I can't read it because my screen got cut off, but I'll just go ahead and memorize it. VRF systems have 5 rating points: EER, IER, COP heating 17, COP heating 47, and SCHE. So you're just picking true or false on this one. It's not a trick question, straight question. No weird thing in there. So like about 73% of people voted. I'll give it a little bit more time. And I'll close it in 5, 4, 3, 2, 1. All right, good. Looks like most people got it correct. 72% of you got the correct answer, saying that yes, those 5 different metrics are all used when rating a VRF system in terms of efficiency. 2 of them are for cooling, 2 are for heating, and 1 is for simultaneous. All right, so let's go ahead and go back to the slides here until that screen pops up. I think we're all caught up on the attendee questions. I was debating on whether leaving this slide in or not, but I went ahead and left it in just to kind of illustrate a little bit. Down on the bottom axis is the amount of heating versus cooling, right? So blue is my cooling line, red is my heating line. This is a heat recovery system, so it's a 3-pipe system that does simultaneous heating and cooling. And I just wanted to leave it on here because it kind of visually points out that when I'm in the full cooling scenario, which is the 0 column there, let me see if I can use my little highlighter thing. When I'm down here, it shows my efficiency for my cooling system. On the opposite side, at the 100% ratio means I'm all in the heating mode. Nobody wants cooling, everybody wants heating. You know, those are my 2 least efficient points. Anything in between there, where I have some zones that want heating and some zones that want cooling, my efficiency is going to improve. My COP is going to get better. It's going to go from 3.5 or 4, depending on what mode I was in this particular example, up to 6, 7, something like that. The perfect scenario being I got, you know, half the people want cooling, half the people want heating exactly. That will give me my most efficient scenario, right? Because I'm just dumping heat from some rooms into other rooms. So that, I know the chart's a little bit different than the text we were talking about, but it kind of visually shows the magnitude and the benefit of being able to have simultaneous heating and cooling. As most of you know, historically, with small DX systems, and VRF systems are small DX systems, we've traditionally encouraged designers not to mix things. Like we would say, don't push the east zones on the same unit as the west zones, and don't mix the interior zones with the south exposure, right? Because the sun is beating on different sides of the building at the time. We basically try to get you to put it into 9 zones, right? North, south, east, west, the 4 corners, and then the core. 9 zones would be perfect. Well, with VRF, we do quite the opposite. When we start doing these VRF systems, and specifically heat recovery VRF systems, we start telling people, well, you know what? The more zones I have calling for the opposite mode at the same exact time on the same unit, the more efficient I get. So if you could, please take some of your interior zones and mix them with your south exposure zones. Please go ahead and mix the east and west guys together because they probably need opposite things at certain points of the year. So it does get a little bit interesting in terms of how we lay a building out compared to other DX systems. I really do want to mix the exposures, unlike a traditional system, to get more simultaneous heating and cooling hours. Let me clear those things off the screen. All right, so when I pick some equipment on that AHRI directory and search for stuff, this is what's going to come back to me in my search. Down at the bottom, it cut off on here, but down at the bottom, it'll tell you how many pages of results you have and how many systems are on there. And there's like 2,300 systems that are rated at this point from those 10 different manufacturers. So there's a lot of stuff. So you do have to put some of these pieces of data in to filter it down. But if we just take the first one, for example, on the left, you get your AHRI certificate number. You can also click on this, and it'll bring up a copy of the certificate that you can print for your customer. It'll tell you if the system is active or not. You can search for non-active things for a certain amount of months, and then they pull them off the website. It'll tell you the brand and the manufacturer. In this case, the brand and manufacturer are the same, but sometimes they have different names. The whole Chevy, GM, Cadillac type thing. The AHRI type, and remember the R means heat recovery system, so all 5 on this screenshot are heat recovery, and the A means it's an air-cooled or an air source system. The rest of the digits don't really matter for our purposes here. The system model number, then the module model numbers. So what that is they recognize that you can take 2 or sometimes 3 of these outdoor modules, these outdoor condensing units, if you will, and bank them together on the same refrigerant network. And typically what the manufacturers do is they give that its own model number when I put 2 modules together, so that way it can have its own rating. So in this particular case, this is a 144,000 nominal BTU system, so it is a 12-ton system, but it's made up of 2 6-tons, 2 72,000s bolted together. So I got 2 6-tons bolted together. I could have 2 6, I could have a 6 with an 8, I could have 2 8s, and so on down the line. So that's why you got different model numbers there. The next thing you'll see is that indoor type. This one is very interesting. There are 3 flavors of things that'll pop up here. You'll have ducted indoor units, you'll have non-ducted indoor units, so like high-wall duct-free split type units or cassette type splits, or you'll have mixed, which means I got some indoor and some ducted and some non-ducted. One of the things that you'll note, if we just for right now look at, actually you can look at any one of the energy values you want, EER, IER, SCH, whatever, you'll notice that the ducted units are always going to be less efficient than the non-ducted units. All right, I'll circle those right now, right? So here's some ducted unit efficiencies. Here's some non-ducted unit efficiencies. And you can see the non-ducted ones, the efficiency always goes up. The reason that is because I have a lot less fan energy because I don't have to overcome the static resistance of ductwork. And it's easier for me to pump refrigerant a little bit further into the zone than pump it into some central air handler and then duct it over. Like we said before, ducting is the least efficient way to move heat around. So the less ducting I have, the more efficient I get. So you will see all of the efficiency numbers, both full load, part load, and combined numbers, all get better. And even this is true on the heating numbers too, by the way, right? They're all going to get better as I go up in efficient, as I get rid of some of my ducted units. And then the mixed ones, ducted and non-ducted in the same system, they're going to be somewhere in between ducted and non-ducted in terms of efficiency. Let me clear that off and we'll keep on moving here. So that's what the indoor type is for and why you have different ones in that bucket. The capacity is how many BTUs that is something that's actually tested at. So yeah, this is a nominal 144,000 BTU system, but in real life it's really 138,000 BTU system. It's just that we like to have things in nice even 6, 8, 10, 12-ton buckets, so that's why the manufacturers do that. The ER, that's our full load cooling efficiency. IER, that was our part load. SCH was our combined heating and cooling efficiency when I have zones mixed together that need opposite things. Then I got my heating capacity, in this case 152,000 BTUs. My COP at 47 degrees, which is indicated up on the top of the screen there. 47 degrees. He's a 3.2 COP, or if you want to think of it this way, 320% efficient. My 17 degree number, he dropped down to only 220% efficient, right? And if I had one that was a whatever, a minus or 0 degree COP number, he'd probably be like 1.4 or 1.5 or something like that if they rated it that way. Clear that off the screen for you too. And then on the very last column is heat recovery, yes or no. In this case, they're all heat recovery units. Farad asks if you can get an EER rating at various outdoor air temperature conditions for simulation purposes. The answer is probably no. You can't get it from AHRI. If you look at the AHRI table real quick, where'd it go? It does show you cooling capacity ER at 95 and at 86. But really, as you're going to see in a little bit, that doesn't correlate to all equipment. It's either 95 or 86, depending on what type of equipment it is, air or water. So you cannot get it from HRI. It is not. They don't give you the individual of these 4 testing points on the IEER, but your manufacturer may be able to get it to you. We'll also talk a little bit about simulation tools in a couple minutes here. So if I clicked on the certificate number, it would pop up something like this. It would tell me the date that I had printed the certificate, which is useful, you know, when you're doing rebates or something of that nature down the road. What my model number is, my brand, etc., like you would expect. Was it with ducted or non-ducted units? My rating points, right? So 1, 2, 3, 4, 5 different efficiency numbers I have, right? 2 for cooling, 2 for heating, 1 for simultaneous. My my cooling BTUs at 95 degrees, my heating BTUs at 47 degrees, and my heating BTUs at 17 degrees. So you can see this guy lost, I don't know what it is off the top of my head, 40% of its capacity as I dropped from 47 to 17 degrees. I'll also tell you when this particular system was rated, right? So this is a November 2013 printing of a June 2013 actual rating data. That way, if you ever have to go back in time or if things change, you know what all your data was based on. I would highly recommend with any system you do on that AHRI directory that you print off the certificate, because things do change and you want to have that most current, or that thing you based it on in your file. All right, let's talk about Ashrae standard 90.1 a little bit. So starting with 90.1 2010, we started putting in categories for VRF systems in there. Prior to that, when you were looking for Ashrae compliance or code compliance, you basically just used the DX split system rating, and it was very easy to hit that with the VRF system. Now VRF has its own category and its own set of 3 tables in the 90.1 book, and those efficiencies, you'll note, are often required a little bit higher than other DX systems. Up on the screen, I'm showing you a air source system, right? So no geothermal or cooling tower loop or anything like that, just an air-cooled heat pump. An air source system in 90.1 2013. 2010 would have the same data, basically, so Actually, it has the same EER and it had slightly lower IEERs. But the IERs are very easy to hit. When you look at most of the manufacturer's data on AHRI, many of them will just barely hit the EER number, and then almost all of them are going to crush the IEER numbers on this screen. It's very easy to hit these part load numbers when you have a variable speed compressor with variable speed condenser fans with modulating EXV valves all over the place and variable speed indoor fans or multi-stage indoor fans. It's easy to crush the part load numbers. As you can see before, the part load on this one we pulled off the website was, I had an EER of 11 and an IER of 20. And he was 118,000 BTUs, so what would he have required? He would have required, right here, that's heat recovery. So he just barely beat the ER because he was 11 and 20. And so he crushed the IER. You're going to find that very true on all these VRF systems. They're really, really efficient at part load. And the good news is most buildings are at part load a good chunk of the year. So VRF systems do get to be pretty efficient in that regard. A couple other things to note. You'll note that there is ratings for both multi-split systems. So that's basically just your regular heat pump. And there's separate ratings for heat recovery. And that's for each BTU range. You'll have one and the other. Right? And in the next BTU range, he'll have both regular and heat recovery. And the next one, regular and heat recovery. You will note in general that if you have heat recovery, your EER and IER numbers get slightly less for having heat recovery. They're basically giving you a credit saying, hey, thanks for doing a great job of doing some of this simultaneous hours. We don't really know how to quantify it for you in the codes, but we're going to go ahead and give you the benefit of the doubt and assume you're doing some simultaneous, and we'll give you a lower number if you have heat recovery, a lower target number. So that comes up a little bit every once in a while. That's the cooling side, right? That table right there. This is the heating side of the equation, right? So you'll notice for this that we have to meet both the Ashrae requirement for 47 degrees outside and 17 degrees outside. Each one of them has a COP that we have to hit. 3.3 and 2.25 in this particular case for 118,000 BTU system, which is what we had a minute ago. What were we at on that one I grabbed? We were at 2.25 and 3.34. 2.25 and 3.34. So we hit the bare minimum on the 17 degree number, and we slightly exceeded the 47 degree number. And you're going to find that for a lot of these systems. It'd be really hard to find a system that does not comply with the Ashrae standard. Most of them do. And you also notice there's less ranges here on the heating side that you have to hit. There's basically just 3 sizes. The small ones are rated in Hspf, although hardly anybody, I would argue maybe even nobody, makes a VRF system that's less than 65,000 BTUs, less than 5 tons, or less than 5.5 tons, so it almost never comes up, right? You will also probably want to know, just take a discussion. I didn't bother putting the screens on here because I didn't want to confuse anybody with what needs to happen, but if you're doing a water source job instead of an air source job, then the tables are completely different than the ones I just showed you. There's a separate table for water source VRF systems, and yet another table for ground source systems. The water source requirements have higher efficiency requirements than air source, and the ground source has higher than water source. It's kind of the way it goes. Very similar to the chiller guys, right? There's certain air-cooled chiller rules you got to hit, and if you have a water-cooled chiller, they give you a harder target to hit, just the way it goes. For whatever reason, on the water source and ground source systems, they only make you rate them for the EER. They don't have an IER requirement. I'm not sure of the reason of that. Maybe the testing isn't caught up with the standards yet, or vice versa, but you'd only have to have an EER they have to hit. And like I said, those EERs are higher. If you have a water source system, that's when you'll use the 86 degree rating point. So when you look at that AHRI directory, we showed 86 degree temperatures on that. That's when you're in a water system. If you're in an air system, they're rated at 95 degree ambient air. If you've got a ground source system, it's rated at 59 degrees. There is one other table that you will find in Ashrae 90.1, and it is completely useless, but many people I've noticed are going to that table and thinking that's the one they got to follow because it's the first one on the 3 pages. That table, when you read the heading of it, that table is actually for cooling-only systems. Nobody that makes VRF is putting cooling-only systems in the U.S. market, so it's completely irrelevant, and there's none of them on the AHRI directory website, so just ignore that first table. It doesn't do anything at all. Skip the first table and go to the heat pump system, because in the U.S., all VRF systems are heat pumps. That makes sense? Andrew, I saw your question, and you'll be fine. We'll talk about it later, but you'll be okay. All right, last couple of things here. We probably got about 5-10 minutes more stuff. The EER, this chart was actually put together by a VRF manufacturer and not one of the ones we rep at our office, another one, but they made this chart to show to compare air-cooled chillers, water-cooled chillers, and VRF. And you'll notice that on their chart, VRF always wins, right? Because they're a VRF manufacturer. Obviously, that's the case. My company, we do air-cooled chillers, water-cooled chillers, and VRF, so we're trying to be a little more agnostic. Every once in a while, even on their chart, it shows the water-cooled winning. Just to be clear, the reason you'll see this on some of the VRF guys' literature and language is that they're taking this green line and this blue line. Those are at the 90.1 minimum conditions for those type of chillers. And actually, specifically, they're the 90.1 2007 minimum conditions, right? Which is very close to 2010. So that's what those are based on. They're showing, yeah, their VRF systems beat those guys, because they usually do, if you're going to use a legal minimum chiller. You can certainly get chillers. You can buy and build chillers that have lines that are way up here like this, that will beat out the VRF system in most cases. That's certainly possible. But the average VRF system is going to beat out the average chiller system if you were buying just the bottom of the barrel average chiller, which a lot of you guys don't do. So let's try to look at this in a little bit different way and try to think of a way we can compare chillers to VRF, even though their rating systems are completely unrelated to one another in real life. And this came from yet another VRF manufacturer, and once again, not one that I rep at my office, but it's a great chart, so I stole it from them, and that's what I do. So on this chart, in this baby bluish, whatever you want to call that blue color, we have the VRF rating systems in terms of kW per ton at different loading points, right? So at 100% load, 50, 25, 10, etc. That's these blue bars here. So I got this first blue bar right there is my VRF system when he's fully loaded, and his line kind of makes this inverted curve down here. That black line represents all my VRF system ratings at 10 different points. Now when I look at my chillers are in green, right? So if I look over here at a 100% loaded chiller, he's using 0.6 kW per ton. My VRF is using 0.9. My chiller is more efficient than my VRF system, right? And that's true for most of these cases. Green is lower than baby blue all the way until I get down to here to this 10-15% range, and then the VRF beats the chiller, right? However, that's not really a fair way to look at it, and this is coming from a company that we do chillers and VRF. The VRF is what I call an all-in rating. It includes all the distribution costs, including the fan energy of the indoor coil, right? The chiller is just the chiller. If I add the cooling tower to the chiller, then I add the yellow band on there. And the cooling tower does really good until I get to really low loads, and the cooling tower can't really ramp down that much more. So I get a pretty big yellow bar over here. Then I got to add in the chill water pumps and the condenser water pumps. That's this light blue and the silver bar. Then I got to add the fan energy in for the air handler, which are these blue bars, right? If I start doing that, now I'm comparing the top of this line to the black line. I'm not a good artist, sorry. Right? Now, in most cases, the VRF is going to win. And this particular example was using a centrifugal chiller with a VFD on the compressor, VFD on the air handler fans, VFD on the water pumps, right? So you can see what's happening here is that in many cases, this blue bar, the fan energy, is definitely the big gorilla in the room. And having a VRF system that doesn't have a lot of fan energy to begin with, and that energy is included in its rating points, is pretty beneficial. And chill water is not a bad way to move energy around a building. It's a really good way, like we said earlier. It's just not quite as good as refrigerant in moving it around. So I think when you look at it that way, you'll see VRF could beat the chilled water systems, even the water-cooled systems, water-cooled chiller systems in many cases. But how do I know what's going to win on a particular job? And that kind of goes back to Syed's question earlier on. How can I rate these things? So the best way to compare systems of different types, and this is not just a VRF thing, but if you want to compare a chiller against a rooftop, it's very hard to do that, right? If I want to get actual numbers involved, I need to basically add up all the costs of everything involved and then add up all the costs of the other thing, everything involved. The best way to do that is with energy modeling and energy simulation. We don't have time to do that today, and obviously it'd be dependent on the software you're using. But I was able to find at least 5 software packages that have what I'm going to call wizards built in to make modeling VRF systems easier. And obviously all these software packages already have tools for modeling rooftops and chillers and air handlers and all that good stuff, right? So these 5 packages do have either modules or wizards or add-ons you can do to model VRF. Are they perfect? No, but they do make it a little easier. And one of them, Energy Pro, even is getting data from the manufacturers themselves and plugging it in. Whereas, for example, like the Carrier HAP one, they use manufacturers' data, but guess whose data they use? They use the Carrier Toshiba data, or the Toshiba Carrier, I should say. And Trane, I don't know it as a fact, but I'm assuming Trane's probably plugging in real data, but it's probably their product line. Energy Pro is nice because it has different products data in there. But that's pretty much what you got to do when you want to compare one system against the other system. All right, refrigerant safety, last 2-3 slides here. Ashrae 15 is our refrigeration safety standard for the country. That's pretty much what everyone in the entire country follows, except the city of Chicago, which has its own set of rules. I'm going to talk about it from the Ashrae 15 standpoint. Just know that if you are in the city of Chicago proper, your numbers will change, as in the examples I'm showing, but the basic theory and premise is going to be the same. So the first question is, yes, Ashrae 15 does apply to VRF systems. I can't tell you how many people I've heard say, no, VRF has an exception because it would be impossible to do it. One, there is no exception for refrigerant safety. It's a safety code. There's no exception, right? You have to do the safety code. 2, I don't know why you would say that because there's multiple zones we don't have to do it. It's even more critical that I pay attention to it on these systems. So yes, you have to follow Ashrae 15 or your applicable local refrigeration code like in the city of Chicago. The first question to figure out for either one of those 2 codes is who's my smallest zone? Because the worst case scenario is that all of the refrigerant in my entire system leaks into one tiny zone and someone dies, right? What's my smallest zone, so I know the smallest amount of volume I have to deal with in case my refrigerant leak was in fact in that room. Question number 2 is, how many pounds of refrigerant do I have in this system? If I have half a pound of refrigerant like you have in your refrigerator, it doesn't matter. If I have lots of pounds of refrigerant, it's going to matter. So how much do I have? So who's my smallest zone, and how many pounds of refrigerant do I have in my system? And by the way, it's not how many pounds of refrigerant were shipped into the condensing unit. It's how many pounds are in my system when it's installed and charged. Once I add 300 feet of pipe, that number is going to be more than whatever came in the condensing unit. Then I got to look up the refrigeration concentration limit. Where do you get that? Well, in the city of Chicago, they publish their own limit. For Ashrae 15, they refer you to another Ashrae standard, because that's what we do at Ashrae to get you to buy more standards. So you look at Ashrae standard 34 to find out what the RCL is, the maximum amount of refrigerant I can have on each individual circuit of refrigeration. In the case of a VRF system, you know, my 2 condensing units outside and my 10 evaporators inside is going to be 1 circuit. For R410A, which is what most VRF manufacturers use in the United States, I'm allowed to have 25 pounds for every 1,000 cubic feet. I'm just going to point out that's cubic feet, not square feet. So you got to multiply the square feet by the height for you guys that are math whizzes. So 25 pounds for every 1,000 cubic feet can leak into one particular space. So who's my smallest zone? If my smallest zone is a 10 by 10 office and it has an evaporator in it, 10 by 10, let's say the ceiling height is 10 feet because that makes the math easy for me, that has 1,000 cubic feet. I can have a maximum VRF system of 25 pounds. If I install one that's 29 pounds, can't do it. I'd have to not install that system or I got to change something, right? And we'll talk about things we can change in a second here. If you have an institutional occupancy, your limit gets cut in half. So my 25-pound limit becomes 12.5 pounds. Institutional occupancy, there's a whole definition for it, but the summary is, do I have a space where people are not able to evacuate themselves on their own? So do I have nursing homes, hospitals, prisons, these sorts of spaces are institutional. A daycare, you could probably argue, is institutional. Right? If I have these types of spaces, my limit gets cut in half. Right? There are some exemptions. If you have a total of less than 6.6 pounds of charge, you do not have to follow this at all. And if you have laboratory spaces, and there's certain rules with that, but certain laboratory spaces don't have to follow it either. All right? But for most of our stuff, offices, schools, that kind of thing, we got to follow it. The easiest way to decide how to follow it is there's an Ashrae Journal article from about 2.5 years ago. If you're an Ashrae member, look it up. It's a fantastic article, and it explains how Ashrae 15 works, and then it gives you some practical tips on applying VRF with Ashrae 15 in mind. Right? These are kind of the summary of those tips. The first thing you can do if you can't meet the 25 pounds per 1,000 cubic feet for one of your zones is get rid of the smallest zone. Right? I'm not saying get rid of the building, the zone in the building, but take it off the VRF system. If you got this VRF system and all the zones are big and you got this one little tiny rogue zone on his own, take him off the VRF. Put him on his own system. Put him on his own split system or duct-free split or something like that, and get him out of the calculation. And then go look at your next small zone. Now, if you got a bunch of small zones, like a dormitory building, okay, that's not going to work. But if you only got one rogue small zone or two rogue small zones, this is a solution. The next thing you could do is you can combine some small zones. If I have two small zones and I combine them into one with a ducted unit, I've just doubled the volume of space that I'm concerned with, right? So obviously half the refrigerant would leak into one zone, half would leak in the other zone, so I would have less of a concern. So I can do that. The penalty, obviously, is now I have one thermostat for two zones, right? So sometimes this makes sense, sometimes it doesn't. If I got two offices, both on the eastern exposure, and they're both 10 by 10 offices, okay, maybe they can work with one thermostat. But I wouldn't want to mix ones that are opposite exposures or a conference room with an office or something like that. But I can duct two zones or more to one unit, and then I've increased the cubic volume that I'm thinking about. I can put the unit above the ceiling, right? So putting a unit as a high wall unit on the wall, on a drop ceiling, I have a certain volume of the room. If I put in a cassette style unit, right, then I have some of my leakage going above the ceiling, some of it's going below the ceiling. So I can increase my total volume that I'm looking at. So instead of a 9-foot ceiling, I have an 11-foot to work with or something like that. That may help you if you're right on the borderline. I can use smaller systems. Instead of one 30-ton VRF for this building, maybe I got to use two 15-ton systems. Or maybe I want to use three 10-ton systems to do the job, right? That way each circuit, if you will, is smaller, and I will have less likelihood of hitting that RCL limit. And then finally, I can interconnect the spaces with permanent openings, right? If I have two spaces and I join them together permanently from an air connection standpoint, then that is one space, volumetrically speaking. So I can increase the volume of the space and hence favor my calculations. Now, just to be clear, they don't say whether shaving doors down it counts as permanent openings, but almost everyone is in agreement that I talked to that shaving the door down does not count as a permanent opening, because you don't know what's going to happen 5-10 years from now when they put new doors in and they don't put them shaved down. You're going to be the liable person. So that is not really acceptable as a permanent opening. Permanent opening would be literally removing the wall so they're physically connected into one zone, putting in transfer grills, putting in jumper ducts, those sorts of things that are not likely to be removed. Shaving a door probably wouldn't count. And then let me just leave you the final note on that. It's not just which zones have an evaporator coil in them. It's which zones have any portion of the refrigeration system in them. So if I decide to take my refrigerant pipe and cut it through the storage room in order to get it over to that other office over there, that storage room is now part of the system. What's the cubic volume of the storage room? He's now a critical zone that I have to pay attention to. So it's not just where the indoor units are located. It's where indoor units are or piping goes through those spaces. All right? I'm going to pop up the last question on here, then I'm going to read some of your guys' questions. All right, here's the last question. True or false, Ashrae 15 allows a maximum of 12.5 pounds of refrigerant per 1,000 cubic feet for all spaces? That's our question. I'm going to launch it right now. Let you guys answer that. Got about 75% voted. I'll give it a few seconds. All right, I'm closing in 5, 4, 3, 2, 1. Close the poll. Show you guys the results here. You guys pretty much got it correct. 87% of you said that's false. It was a bit of a trick question, right? The keyword was all system types. That 12.5 pounds is just for institutional types. Regular types like offices and stuff like that would be double that at 25 pounds. Let's answer a few of the questions that came up at the very end there. Jonathan has a good question that I forgot to mention. So Jonathan asks if that chart I had showed, I'll put it back up for you guys. Well, let me get rid of the other thing. If this particular chart I got up on the screen accounted for the ventilation costs associated with the VRF, and no, it does not account for that. That is a good point, and that, in terms of this chart, is in favor of the VRF system. In many cases, as you might expect, a VRF system is coupled with a dedicated outside air unit, so those green or those baby blue bars for VRF would go up somewhat for the ventilation equipment, if you will. Now, I would argue that it's still less energy than the dark blue bar for the AHU because I'm only moving 25-30% of the total air volume than I would have been moving with the all air system. But yeah, that's a good point, Jonathan. And there's probably two reasons it doesn't have that. One, this chart was made by a VRF manufacturer, right? And two, many VRF systems are not being installed in buildings that have DOAS systems. The majority of systems that I've worked on have natural ventilation systems. Now, I'm not a fan of natural ventilation at all. In fact, I'm sort of opposed to it. But a lot of them are installed in those cases because a lot of the VRF systems that I personally have worked on, we're going into buildings that have heating-only steam or hydronic radiators, and we're adding cooling systems, and they're currently permitted under codes that have natural ventilation, and they're keeping the natural ventilation. Right? So that's one of the reasons. Now, I'd argue that hardly anyone opens their window, but that's a separate debate. But good point, Jonathan. This chart on the screen did not include ventilation costs on a VRF system. Let's see what Tyler's question was. Does the water-cooled chiller versus the VRF system account for water or air-side economizer? And no, it did not account for that in this particular case. Probably for the same reason the chart was made by a VRF guy. However, a lot of spaces can take advantage of a water-side economizer. Excuse me, I'm sorry, Tyler. It does take into account an air-side economizer. It did not take into account water-side economizing, if that makes sense. Because this particular example was based on VAV air handlers. So it did include air-side economizer in the energy model. It did not include a water-side economizer, which is what you would have done if you had like a fan coil type job. Bill asked the same thing about the ventilation costs with the VRF, so we already answered that. Okay, I don't understand Andrew's question. Let's go to Farad's question. Farad asks, what are the requirements if the refrigerant lines are running through corridors? All right, so that would be the same thing. So my smallest space, or this corridor, let's say, I'd have to look at the volumetric space of the corridor. So whatever, let's just say the corridor is 100 feet long to make my math easy, and let's say it's 5 feet wide and 10 feet tall, right? So it's 100 times 5 times 10. I probably shouldn't use a calculator for that, but it's 5,000 cubic feet if that's my corridor size. If I got refrigerant pipe in the corridor, I got to make sure that I'm under, in this case it's 5,000 cubic feet, so I have to be under 125 pounds of total refrigerant charge, which I should be able to do fairly easy. So unless you have a very small corridor, this is probably not going to be an issue at all. But it is one of the spaces you would have to look at if your refrigerant lines do run down the corridor of the building. Let's look at Andrew's question. Andrew's asking about 100 cubic feet. Is that only for occupied spaces? Does that include unoccupied spaces like mechanical rooms? Yes, it does include unoccupied spaces, which is why when we have chillers in mechanical rooms, it typically kicks in the rules where we have to have refrigerant monitoring systems. And by the way, I should have mentioned that too, right? So when I have these tips on here of ways you can comply with Ashrae 15, if you're above the limit, the other thing you could do is you could put refrigerant monitoring in, right? And then I can be as high as I want as long as I have refrigerant sensors that'll alarm people and tell them to get the heck out of there. Now, for a VRF system, that's not very practical because I have so many zones to think about. But for a chiller room, a mechanical room, that makes a ton of sense, right? Because it's all in one room, I only got to buy one sensor. But for a VRF distributed system, it doesn't make sense. But yes, Andrew, those limits are for all spaces, including the mechanical room. Let's see. Larry says different manufacturers have different piping arrangements, 2-pipe and 3-pipe. How do you know what the refrigerant weight is after it is installed? That's a great question, Larry. So I can only speak for two manufacturers that we deal with at my office. We deal with Panasonic/Sanyo, and we deal with Toshiba Carrier. I know we have to have 4 names for 2 things, but that's what we got. In both of those cases, the software tools that we use to lay out the system will calculate the refrigerant volume required, and we give that volume to the installing technician so we can weigh that amount of refrigerant into the system. Now, the hard part about that is that if in the field they decide to run the piping a different way than we meaning you and I, agreed on laying it out, then we need to know that from them so we can give them a different refrigerant calculation. But that data gets calculated by the refrigerant piping design software is where you get that number from. So you'll have a good guess of what it's going to be when you design the system, and then as long as they don't pipe it differently than what you designed, you will be fine. Lucas asks about refrigerant relief requirements on Ashrae 15. I'm not so up to speed on that, but let's see if we can. I'm going to save your question for last, and I'm going to pull it up on the screen. I'll pull up Ashrae 15, and we'll look it up. Gustavo, how does it work when you run refrigerant pipe through chases as far as being your smallest space and therefore does not dictate your volume? I would argue that a space would not have occupants in it at any point in time, right? A corridor will have occupants in it. A vertical chase going up your building is not going to have occupants in it, and if they are, they're going to be the mechanical contractor working on something, but not a normal, quote-unquote, unarmed occupant. So I would argue that the chase is not something I have to consider for smallest volume because there's no people in there to have a problem. Andrew asked, does the water-cooled chiller have outdoor energy included? Yes, that was included in the air handler portion of the water-cooled chiller calculation. Tyler asks, so Tyler's asking an interesting question. He's asking what capacity, what tonnage of a system would I be at approximately with 25 pounds of refrigerant? So unlike a rooftop or a chiller where there's a certain amount of refrigerant for a certain tonnage model number, VRF system is going to be all over the board because it's a split system. So depending on whether I have 100 feet of pipe or I have 600 feet of pipe makes a huge difference in my volume. With that being said, it's usually fairly easy to get under the requirements if you're talking about small systems, 6, 8, 10 tons. When you go above that, it becomes more and more critical that you pay attention because you're probably going to be above the refrigeration volumes in some of your zones. But I can't give you a tonnage answer, Tyler, because it depends on how much pipe you're going to run. Robert's got a question about his local inspector, so we'll try that. It says that if you use a refrigerant monitor, everyone who enters the room need OSHA level training to know what to do if the alarm triggers. This is nearly impossible. He also says the room needs signage to that effect as well. Robert, you are correct. You do have to have the signage. You also have to have the alarming. I don't know about the training portion of that. I believe it, and if your inspector says it, then I don't know, you got to do it. But you are correct. You'd have to have an alarm inside the space. You have to have an alarm outside every single door to the space, right? So no one can enter there if there's an alarm condition. And the alarm has to be audible and visual, so a strobe and a horn. And you do have to have signage. I'm not sure about the training piece, but maybe you have to do that as well. But as soon as you say the other things, I got to put in a sensor and alarming system in every room, and then put alarming system outside every door to the room. That pretty much makes it prohibitive for anything other than a mechanical room. Ron's asking what type of refrigerant piping can be used, hard K or ACR, annealed soft K or ACR copper. I'm going to go with the manufacturer's recommendation for the answer on that, Ron. Most time what they want to see is soft lines, continuous. They'd really like you to take out 100-foot line sets and roll them out and use that. So they really want you to go the ACR route. They will allow you to use hard pipe. Most manufacturers will, but then they start changing the rules and the maximum distance that you can go. Because every time we braze those pipes together, there's going to be a little bit of a bump there, right? So a little bit more friction, and some of those distances that they can go are friction dependent. So usually you look at the rules for the VFR manufacturers, and they'll be directing you to use ACR. That doesn't mean they'll prohibit you from using hard pipe. It's not ideal to use 20-foot sticks of pipe and get the same amount of links out of it. So for a lot of systems, it won't matter. I know in the Chicago area, the union guys like to use hard pipe and not use the pre-manufactured line sets. You can use both. The rules may change depending on your manufacturer. All right, I think I got all the questions answered except for one guy. I'm going to go back to Lucas's question about the refrigerant relief requirements of Ashrae 15. Anybody else wants to stay for that, great. You can certainly stay online. But I'm going to go try to pull up his answer, and anybody wants to hear it can check it out. So let me pull it up, Lucas, here. Let's pull up. That's not the right one. Pull up. That's not the right one. I got a lot of Ashrae standards open at one time here. All right, here's 15. Only because I personally don't pay attention to that particular requirement much. Let's see if I can just keyword search it. That'll take too long. Let's see if we can go relief valve. Definitions. So many pressure relief valve things in here. I don't know, Lucas. I'm going to have to take more time and look it up, and then I'll email you the answer. I don't know where the relief valve requirement is on these 38 pages, but I'll find the answer and I'll email it to you. All right, everybody else, thank